Every tale commences somewhere, and this holds true even for the narrative of the cosmos. Approximately 13.7 million years ago, an enigmatic occurrence propelled the universe into motion, marking the advent of the Big Bang. An extraordinary event that gave rise to every atom, star, and galaxy. However, what unfolds here is uniquely ours, a saga spanning millennia where we've endeavored to construct a vision of the universe. This endeavor, guided by the principles of science, has allowed us to fathom our place within the vast cosmos. Over thousands of years, we've documented our celestial observations in volumes that could easily populate a library. The edifice of knowledge we've erected regarding our universe encompasses its origins and contemplates its eventual conclusion. So, where does our narrative commence? Let's embark on this journey from the very outset. Let's delve into the genesis, starting with the monumental event known as the Big Bang. The concept of the Big Bang serves as a framework for understanding the cosmic evolution, an unfolding narrative that illuminates how the universe transformed in the blink of an eye. The very nature of what sparked this cosmic genesis remains an unsolved puzzle to this day. As we peer into the vastness of the universe and contemplate distant galaxies, a mesmerizing panorama unfolds. Everything appears to be receding from us, propelled outward at astonishing speeds. We string that all the way back. We glimpse a singular moment, perhaps 13 or 14 billion years in the past, where all matter was inexplicably condensed into an inconceivably dense point. The Big Bang stands as our prevailing theory, a testament to our attempts to decipher the universe's inception. For an extended period, contemplation of the universe's origin was not a common pursuit. Some didn't dwell on it, while others assumed the cosmos had perpetually existed, an everlasting entity shrouded in mystery. Initially, even scientists hesitated to embrace the concept of the Big Bang. Originally intended as a somewhat derisive term, the name itself poses a paradox. It wasn't particularly big, considering our belief that the universe originated from a singularity, and there was no literal bang since there was no air to transmit vibrations. Today, the Big Bang theory is a well-established pillar of science, widely accepted and understood. However, acceptance and comprehension are distinct realms. While the Big Bang theory has solidified its place in our understanding of the universe, it hasn't yet unraveled all the mysteries science seeks to answer about the birth of our cosmos. Conventional Big Bang theory remains silent on what triggered the bang, why it occurred, or what transpired before it. At this very moment, we find ourselves in the aftermath of the Big Bang. Everything what we see and hear and taste and smell and touch is aftermath. This is the Earth, a marvel of silicon and oxygen encasing a metallic core. Its surface is dominated by vast oceans, fostering a diverse array of life. In a rhythmic dance, the Earth completes a full rotation every 24 hours, while encircling the radiant star known as the Sun, completing an orbit every 365 days. The Sun, a radiant giant predominantly composed of hydrogen and helium. With a scorching surface temperature nearing 10,000 degrees Fahrenheit, this cosmic powerhouse converts a staggering 700 million tons of hydrogen into 695 million tons of helium every second. This celestial luminary is at the heart of our solar system, which took shape approximately 4.5 billion years ago. This system has 8 planets, from the sweltering Mercury to the frigid Neptune. Our solar system is no static entity. Hurtling through space at a staggering 134 miles per second, it is part of a vast congregation of stars and stellar systems. This congregation, known as the Milky Way galaxy, around 200 billion stars. Among these, an estimated 6 billion may harbor planetary systems akin to ours. Our solar system, orbiting the center of the Milky Way on one of its outer arms, is just one member of a grand ensemble. The Milky Way is merely one among the vast expanse of more than 125 billion galaxies, constituting the observable universe. Indeed, the universe is colossal, and its enormity continues to expand. If we rewind time, we can witness the universe contracting, shrinking from a cosmic scale to a galactic one, then to the dimensions of our solar system, and further still until everything is confined within the confines of a studio, a coffee cup, and ultimately an atom. The vastness of the universe unfolds before us, a cosmic narrative expanding across unimaginable scales. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future? And how will they die? If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. This is the Milky Way, our galaxy. Approximately 12 billion years old, the galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars first and foremost. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years. This is how far light can travel in a year. Our galaxy's diameter is over 100,000 light years, and we're now located at a distance of 25,000 from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our own cosmic backyard and much bigger than Andromeda. But M87 is tiny compared to this giant. 6 million light years across, IC 1011 is the biggest galaxy ever found. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous. But why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.7 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time. So galaxies must have come from that very early universe and formed from it. For stars to form, and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together because to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble, the light we see from distant galaxies now. However, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots. They are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust, gas, and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source. And our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars, as far as we can tell. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations, like the Whirlpool Galaxy, then over billions of years develop into more orderly forms. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior. And they found out: a black hole. And not just any kind of black hole, but it's a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings, much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the sun, the stars also move due of gravity. What we discovered was a bizarre and violent environment. At the center of our galaxy, everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. So, is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light years. That's many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. So what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was at action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he grated on the astronomical community. And this is a brilliant idea. But he was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. And the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true, they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters, containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, It's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The two galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda, as we know it, will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide. But this age of galactic cannibalism will eventually pass. Because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy. Neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities. We used to only know about the planets that circled around our sun. But now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun's system. But now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are huge, rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star they're burning up. One thing is clear. No 2 planets are the same. Each one is unique, but most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So, at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with the cake. Then you'd put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way, depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then, it has enough gravity to crush it into a sphere. Any smaller, and it stays in irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things, like most metals, fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now, they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense. So, it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal, rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials. But each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. And that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye, and you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So, radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens. As the Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then, big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry and there's not much going on. So why have the two planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only the atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So, not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field. And it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. And that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop. The flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere and the water evaporated. Mars turned into a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water, frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big. Because there was so much ice and gas, their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all four of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons. Some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside, far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely, gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So, it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So, how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the Sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So, water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So, it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars. and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain: there are billions of planets out there waiting to be discovered. Venus is nearly identical to Earth in size, making it one of our most similar neighbors in the solar system. With a mean radius of about 3,760 miles or 6,052 kilometers, it's approximately 95% the size of Earth. Its mass is about 81.5% that of Earth. This similarity in mass and size means that Venus also has a comparable density to Earth, approximately 5.24 grams per cubic centimeter, implying a similar rock-iron composition. Venus and Earth have a comparable structure, a central iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles or 3,200 kilometers in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axis in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This is a phenomenon that isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. The solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles or 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there's currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, 96.5%, with most of the remainder being nitrogen. However, there are also traces of other gases, such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers. The troposphere, extending from the surface to about 40 miles up, the mesosphere stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles, due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxua Montes, rising 20 kilometers, about 12 miles above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle and arachnoids, circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet, and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus, using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system. Its vibrant stripes and prominent great red spot making it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones, characterized by lighter-colored clouds. Conversely, its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that's been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It's thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. The exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter, but also sheds light on the broader principles governing atmospheres, including our own. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is believed to have an ocean beneath its surface as well. Jupiter was known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system. Although much fainter and smaller, Jupiter also has rings composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. What if we could peer into the distant future? 300 million years from now, what would Earth look like? How would our planet's continents, climate, and life forms evolve? The answers might surprise you. For as long as we've studied Earth's history, we've been captivated by its deep past. The rise and fall of continents, the evolution of life, the dramatic shifts in climate, all written into the rock and fossils beneath our feet. But what if, instead of looking back, we turn our gaze to the future? Our planet's story is far from over. The same forces that have shaped the world for billions of years are still at work today, and they'll continue to sculpt the future Earth we may never live to see. We are the first species in Earth's history with the ability to predict the future, at least in part. Through science, we've glimpsed what lies ahead. Worlds with unfamiliar ecosystems, transformed climates, and even continents that will shift and merge. So, what will Earth look like in 10,000 years, 10 million years, or even 300 million years? The answers depend not only on the planet's natural processes, but also on the decisions we make today. Join us as we embark on a journey through time, exploring the possibilities of Earth's distant future. Our journey begins not millions of years into the future, but just 10,000 years from now, a blink of an eye in the grand timeline of our planet. The world of 10,000 years from today will be shaped largely by the choices we make in the coming decades. If we continue to release vast amounts of carbon into the atmosphere, the Earth we leave behind will be drastically different from the one we know today. Scientists have studied multiple scenarios for our future climate. In the worst-case scenario, global temperatures could rise by over 7 degrees Celsius, recreating the conditions last seen during the Eocene epoch, more than 50 million years ago. The result? Sea levels could surge by over 50 meters, swallowing entire regions and redrawing coastlines. Imagine this future world. Many coastal cities we know today, places like Florida, the Netherlands, and large parts of Southeast Asia, may be submerged beneath the rising seas, reshaping global coastlines. But the changing climate won't just affect the land and sea. Life itself will be forced to adapt. History has shown us that during periods of rapid warming, mammals tend to shrink. For example, 56 million years ago, during the Paleocene-Eocene thermal maximum, the earliest horses shrank by nearly 30% as temperatures rose. In the future, the descendants of today's mammal may also become smaller, adapting to the heat. Smaller bodies release heat more efficiently, a survival trait that might once again emerge as Earth's climate shifts. Could this be the future of our planet's ecosystems, where shrinking species fight to survive in an increasingly warmer world? And while we're on the topic of evolution, who knows? Maybe we'll even see the return of creatures like Titanoboa, the gigantic snake that roamed the Eocene's tropical rainforests. But that's a story for another time. This vision of Earth just 10,000 years from now depends largely on what actions we take today. The forces of nature are powerful, but our decisions will shape the planet's next chapter in ways we're only beginning to understand. Now, let's travel farther into the future, 10 million years from now. What does this more distant Earth hold for us? By this point, the world will have changed in ways we can only begin to imagine. One of the most dramatic transformations in Earth's landscape may be happening right now beneath our feet. In Eastern Africa, the continent is slowly splitting in two, driven by tectonic forces deep within the Earth. The Eastern African Rift System has been active for millions of years, gradually separating the Nubian Plate from the Somalian Plate at a speed of just 7 millimeters per year. But over the next 10 million years, this snail's pace could finally result in a monumental event: the creation of a new ocean. As the two sides of the continent split, water from the Indian Ocean will flood the widening rift, carving out a new sea and isolating a huge landmass that was once part of mainland Africa. A new island, a Madagascar 2.0, will be born. Islands have always been hotspots for evolution, where species adapt to their unique surroundings in surprising ways. From dwarf elephants to giant lemurs, history has shown us that isolation breeds innovation. In this new island's future, we might see species evolve in ways that defy our expectations, creatures unlike anything we know today. But what if the rift never finishes the job? Sometimes rifts fail. 1 billion years ago, North America almost split apart at the mid-continent rift. The process stopped, leaving behind a scar that still stretches across the landscape today. Could the Eastern African rift suffer the same fate, becoming one of the planet's largest failed rifts? If so, Africa might remain intact for millions more years, the rift eventually closing up as tectonic activity slows. Whether the rift succeeds in creating a new ocean or fizzles out, only time will tell. But one thing is certain: the Earth's tectonic forces will continue to reshape our planet in ways we can't fully predict. Now, let's take an even bigger leap into the far future, 300 million years from today. By this time, our planet's continents will have undergone one of their greatest transformations yet, as they slowly merge into a new supercontinent. Earth's tectonic plates are constantly moving, reshaping the surface in a slow but unstoppable dance. Every 600 million years or so, this movement causes the formation of a supercontinent, a single massive landmass that brings most of the world's land together. The last supercontinent, Pangaea, broke apart around 180 million years ago. But in the future, the continents will come together again. This time, the Pacific Ocean will close up, replaced by a new supercontinent already named Amasya. Amasya will form from the collision of Australia, Asia, and the Americas. As these landmasses gradually drift together, the Pacific Ocean will disappear, bringing an end to the largest ocean on Earth. In this new world, the continents we know today will be unrecognizable, merged into one vast, interconnected land. But life on Amasya will face its own challenges. Supercontinents tend to have vast, arid interiors, far from the moderating effects of the ocean. As a result, Amasya's center may become an inhospitable desert, much like the interiors of previous supercontinents. Species living here will need to adapt to extreme heat and dryness. What kind of life could thrive in such an environment? While we can't predict exactly what species will exist in this distant future, history gives us some clues. The early dinosaurs, for instance, emerged and thrived on Pangaea, evolving into a wide range of incredible species that adapted to all kinds of environments. In 300 million years, evolution will once again respond to the new conditions of Amasya. Perhaps entirely new kinds of creatures will emerge, shaped by the harsh, dry interior and the cooler, wetter regions near the coasts. One thing we do know for certain is that this supercontinent won't last forever. The cycle of supercontinents forming and breaking apart has been happening for billions of years, and Amasya will eventually meet the same fate. It's only a matter of time before tectonic forces pull the continents apart again. As we look ahead to this far future, it's a reminder that Earth is always changing, constantly reshaped by the forces beneath its surface. The story of our planet is far from over, and Amasya will be just one chapter in its ongoing evolution. As we journey through Earth's distant future, one thing becomes clear. No matter how much we study the past, predict tectonic shifts, or model climate change, there are limits to what we can know. Evolution is a complex and unpredictable force. The life forms that will inhabit Earth 300 million years from now are beyond our ability to fully comprehend. But one thing is certain: life will continue to adapt, finding new ways to thrive in environments that would be unimaginable to us today. What will these new life forms look like? Will they be the descendants of today's mammals, birds, or reptiles? Or will entirely new branches of life evolve to dominate the future Earth? The answers remain a mystery, hidden in the deep future. Just as dinosaurs dominated Pangaea and then vanished, replaced by mammals in the blink of an eye, the future inhabitants of Amasya will evolve and adapt to their world's unique challenges, until the next great shift changes the course of life once again. Looking into the future of Earth is a humbling reminder of how temporary everything is. The continents we know today, The species we are familiar with, even humanity itself, all are fleeting moments in the grand story of our planet. But even in the face of immense change, there is beauty in Earth's resilience. Life has endured for billions of years through ice ages, mass extinctions, and the shifting of continents. And life will continue to endure, evolving and adapting to whatever the future holds. The story of Earth is far from over. There are many more chapters still to be written, and while we can't predict all the twists and turns, we can be sure that our planet's legacy will continue long after we're gone. As we look ahead, remember that the choices we make today will leave a lasting mark on the future of our planet. So, what kind of Earth will we leave behind for the life forms of tomorrow? In this video, you will discover the surprising reason why fire exists only on Earth and nowhere else in the universe. Could it be a secret force unique to our planet? Earth is often known as the blue planet due to its oceans and abundant water, a feature vital to sustaining life. However, what often goes unnoticed is that Earth is also a fire planet, the only known place where fire can naturally occur as we understand it. Though there are volcanic eruptions, lightning storms, and even the sun's searing heat, these phenomena don't qualify as true fire. Despite their fiery appearance, none of these phenomena involve actual flames. The sun, for instance, is a massive sphere of hydrogen gas and plasma, where nuclear fusion takes place, but no fire is involved. Similarly, while volcanoes release scorching molten rock, magma itself isn't burning. And as for lightning, it's simply a powerful burst of electricity, not fire at all. Fire, as we know it on Earth, requires a unique combination of heat, fuel, and oxygen, a balance that exists only on our planet. While heat and fuel exist in other parts of the universe, the critical difference is the availability of oxygen in Earth's atmosphere. This essential element allows combustion to happen. The presence of fire on Earth is linked to the planet's atmospheric evolution, which took billions of years. Once fire became part of Earth's environment, it began shaping ecosystems, landscapes, and even the evolution of life. Fire has influenced plant life and helped shape the Earth's surface in ways unique to our world. Without fire, Earth would be a very different place, and life as we know it might not have developed in the same way. This intricate relationship between fire and life adds to what makes our planet truly exceptional. Fire exists on Earth thanks to the presence of oxygen, a crucial element for combustion. However, Earth's atmosphere wasn't always oxygen-rich. Billions of years ago, gases like methane, water vapor, and carbon dioxide dominated the air, making it impossible for fire or complex life to exist. During this early period, life was in its simplest form, and the planet's atmosphere was inhospitable. The oceans played a key role in changing this. Early life forms, such as cyanobacteria, began producing oxygen through photosynthesis, slowly transforming the environment. For a long time, the oxygen released was trapped by reactions with elements like iron, forming compounds such as iron oxide that settled on the ocean floor. It took millions of years for oxygen to accumulate in the atmosphere, paving the way for both fire and more complex life forms to emerge on Earth. Oxygen alone doesn't create fire, but photosynthesis transformed the atmosphere, making combustion possible. Without these early microscopic life forms, oxygen levels needed for fire might never have emerged. The rise of oxygen not only allowed complex organisms to thrive, but also enabled fiery reactions that shaped ecosystems and species. The buildup of oxygen in Earth's atmosphere was a slow process, taking hundreds of millions of years. A critical turning point, known as the Great Oxygenation Event, marked a new era for life and the conditions that allowed fire to exist. Before this event, most of the oxygen produced by cyanobacteria was absorbed by Earth's elements, particularly iron, which formed iron oxide deposits on the ocean floor. For nearly 1 billion years, oxygen levels remained low due to this absorption. Eventually, the reactive elements became saturated and oxygen began accumulating in the atmosphere. This rise in oxygen allowed advanced life and combustion to thrive. However, it also caused the extinction of many anaerobic organisms that could not survive in an oxygen-rich environment, drastically transforming Earth's ecosystems. The Great Oxygenation Event was a major leap forward for Earth. The rise in atmospheric oxygen allowed complex life forms to emerge and laid the foundation for fire to become a natural force. However, fire couldn't ignite immediately. There also needed to be fuel, which required plants to move from oceans to land. At that time, life was still mostly ocean-bound, and the land was barren, lacking the plant material needed for combustion. It took millions of years after the oxygen buildup for plants to colonize the land, providing the fuel necessary for fire to exist. This evolution of plant life, combined with an oxygen-rich atmosphere, set the stage for fire to ignite and transform ecosystems. The Great Oxygenation Event wasn't just about oxygen. It was a pivotal shift that paved the way for fire to shape Earth's landscapes and life forms, marking a significant milestone in the planet's history. After the Great Oxygenation Event, Earth had the crucial element for fire, oxygen. However, fire didn't appear immediately, as it requires not just oxygen, but also fuel and sufficient heat to trigger combustion. Fire is a chemical reaction between oxygen and organic fuel, producing heat, light, and gases like water vapor and carbon dioxide. The best fuels, rich in carbon and hydrogen, come from plant life, which was still in its early stages after oxygen levels rose. The first plants on land were small, simple organisms such as mosses. Over time, these evolved into larger, more complex plants, providing the fuel needed for fire. The key ingredient in plant cells, cellulose, became the primary fuel for fires. As land plants grew in size, they produced more cellulose, creating the right conditions for fire to thrive. Heat, the third requirement for combustion, was typically provided by lightning. As plants spread across the continents, lightning storms sparked fires in dry vegetation. These early wildfires, fueled by oxygen and plant material, were Earth's first true fires. Once fire appeared, it became a transformative force. Early wildfires did more than burn vegetation. They cleared land, recycled nutrients into the soil, and influenced plant growth. Some plants even evolved to depend on fire for survival, with traits like thick bark to resist flames or seeds that require heat to germinate. These adaptations highlight fire's deep connection to life on Earth. As fire spread, it reshaped ecosystems. Fire-tolerant species thrived, while less adapted plants were pushed out, leading to the development of fire-adapted ecosystems like grasslands and savannas, which still rely on regular fires today to maintain balance. Combustion, the process that makes fire possible, has been a crucial factor in shaping Earth's ecosystems. It allowed fire to become more than just a destructive force. It became a creative one, renewing and reshaping landscapes. Fire's presence on Earth was the result of millions of years of biological and geological processes, shaping the planet and life itself in profound ways. Early land plants like mosses and shrubs provided the first fuel, but as vascular plants emerged, allowing for taller growth and more efficient nutrient transport, fires became widespread. During the Carboniferous period, about 300 million years ago, high oxygen levels made wildfires more frequent and intense, burning across vast forests. These wildfires played a crucial role in developing ecosystems. Forests, rich in cellulose and highly flammable, fueled massive fires that cleared land, recycled nutrients, and created space for new plants. Wildfires were not only destructive, but also rejuvenating, balancing life on Earth by both clearing and fostering growth in the landscape. The fossil record from ancient times reveals large-scale fires, evidenced by fossilized charcoal deposits. These remnants show that fire was a frequent force in early forests, with thick layers of charcoal still found today. Fire didn't just destroy, it also drove evolution. Plants that survived or thrived in fire-prone areas had a significant advantage, leading to fire-adapted species. Some evolved thick bark for protection, while others developed seeds that required heat to germinate, allowing fire-tolerant plants to dominate. Wildfires also influenced animal evolution. Animals in fire-prone areas had to adapt by avoiding fire or exploiting habitats created after a blaze. This dynamic environment pushed both plants and animals to evolve quickly. By the Permian period, about 250 million years ago, fire was a well-established force. Trees with seeds allowed forests to spread, providing more fuel for wildfires, which helped maintain ecosystem balance by clearing old growth for new life. As wildfires became a regular feature on Earth, they played a key role in maintaining balance and driving the evolution of species. Grasslands, for instance, depend on regular fires to prevent overgrowth by trees. Fires clear away dead plant material, allowing new grasses to flourish. Grasses have evolved to withstand fire, with their roots protected underground while dry, above-ground material burns. This process returns nutrients to the soil, fostering healthy, nutrient-rich growth. Animals in these areas have also adapted. Prairie dogs, for example, shelter in underground burrows during fires, and birds take advantage of the cleared landscapes to hunt. Fire creates opportunities for these species to thrive in the post-fire environment. In forests, fire helps prevent the buildup of dense underbrush and dead material, reducing the risk of large, uncontrollable fires. Smaller, regular fires clear the forest floor, encouraging new plant growth and maintaining open areas for sunlight to reach the ground. Some trees have evolved to depend on fire for reproduction. Certain pines have cones sealed with resin that only melt and release seeds when exposed to fire's heat. This ensures the seeds are dispersed in a nutrient-rich post-fire environment with reduced competition for sunlight and resources. Even in ecosystems like temperate forests, fire plays a vital role by controlling invasive species and disease, which helps maintain biodiversity. Without fire, these areas can become unbalanced. Some animals also benefit from fire, such as beetles that lay eggs in charred wood or deer that graze on fresh shoots after a fire. In places where fire suppression has been practiced for years, overgrowth can occur, leading to resource competition and ecosystem decline. Reintroducing controlled burns can restore balance and health to these areas. The relationship between fire and life is mutually influential. While fire shapes ecosystems, life also impacts fire. Grazing animals, for example, can reduce fire intensity by keeping grasses short, while dense, dry vegetation fuels larger wildfires. Thus, life helps regulate fire just as fire regulates life. Fire has also been essential to human evolution, providing warmth, protection, and a tool for cooking, agriculture, and land management. The control of fire enabled early humans to shape their environment and expand across the globe. Human activity has altered the natural fire cycle, often suppressing fires to protect settlements. This has led to overgrown forests that are more vulnerable to large, destructive wildfires. Ecologists now recognize the importance of reintroducing fire through controlled burns, which mimic natural processes and maintain ecosystem balance. Fire is both destructive and regenerative, crucial for promoting biodiversity and renewing ecosystems. Without it, Earth's landscapes would be fundamentally different, and life would not have evolved as it has. Fire and life are deeply interconnected, with fire shaping evolution and ecosystems, and life influencing fire's spread and behavior. Understanding this relationship is vital for managing fire in a way that balances human needs with the health of natural ecosystems. The Earth is shaped by its oceans, playing a vital role in supporting life. Without these oceans, life as we know it would not exist. While we used to believe that Earth's oceans were unique, recent discoveries have shown that oceans are not exclusive to our planet. Surprisingly, similar oceans have been found in various locations within our solar system. Scientists are embarking on an extraordinary quest to explore unlikely places in the hopes of discovering new forms of life. It's fascinating how life continually surprises us with its remarkable ability to exist in unexpected places. Water is incredibly important, and it has guided scientists in their search for life in our solar system. All living things require water. It's a common factor for all forms of life on Earth. Oceans, being suitable environments, provide the necessary conditions for life to develop and survive. Wherever we find water on Earth, whether it's freezing cold or scorching hot, we also find life. Considering this, scientists established a simple criterion for the search for extraterrestrial life: find a liquid ocean. However, within our solar system, it initially seemed that there were no such oceans beyond Earth. The concept of the Goldilocks zone suggested that a planet needed to be at just the right distance from the sun for water to exist in a liquid state on its surface. Earth was perfectly situated, while Venus was too hot due to its proximity to the sun, and Mars was considered too far away. Exploring the possibility of water on Mars has been a captivating endeavor for scientists and space enthusiasts alike. The red planet, with its barren and desolate surface, has long been a focal point of planetary exploration. In recent years, the quest to find signs of liquid water or evidence of its historical presence has gained momentum. This pursuit is not merely a scientific curiosity. It holds the key to unraveling the mysteries of Mars' past and present, and perhaps uncovering the potential for extraterrestrial life. Despite our extensive knowledge about Mars, gathered over decades of exploration, the evidence so far suggests that Mars is dry, cold, and seemingly devoid of life. However, the question arises: has Mars always been this way? Interestingly, scientists are searching for evidence of an ancient Martian ocean in one of the driest places on Earth, the Atacama Desert in Chile. The connection between Mars and Atacama lies in their extreme dryness. Mars is known for being very dry, and Atacama is among the driest places on Earth. In fact, the relative humidity measured by the Curiosity rover on Mars is nearly the same as what we experience here in this desert. Surprisingly, the lack of water in the Atacama makes it an ideal location to build one of the world's largest telescopes. Water in the atmosphere could significantly hinder the telescope's ability to detect water and other substances. Scientists are specifically searching for water and organic materials, so they choose places devoid of these elements, like deserts, to avoid contamination when observing the atmosphere. When observing Mars through a telescope, it becomes evident that there is water on the planet, currently frozen solid at the poles. However, the Martian landscape suggests past shaping by liquid water, raising questions about the amount of water that once existed on the planet. The mystery started to unravel in 1984 when scientists made a fortunate discovery in another desert, the coldest place on Earth, Antarctica. They found a remarkable meteorite of Martian origin, and its analysis provided the key to understanding Mars' watery history. Through meticulous analysis, scientists determined that the meteorite was an astounding 4.5 billion years old. This meteorite held crucial chemical information, a fixed isotopic signature reflecting the amount of water present on Mars 4.5 billion years ago. Although this signature alone may seem insignificant, its value became apparent when scientists measured the current water content on Mars. By comparing the isotopic signatures of recent rocks with those of the ancient meteorite, a wealth of information was unveiled. The significance of the enormous telescope comes into play here. Its remarkable power allows it to detect water molecules on the planet's surface. Armed with precise measurements of Mars's present water content, scientists could make a remarkable calculation. They extrapolated back in time and concluded that there was nearly 7 times more water on Mars in the past than there is today. To understand this transformation, scientists looked at Mars' topography. The planet has low plains in the north and high-altitude plains in the south. In terms of topography, if water were to flow, it would naturally move towards the lower northern plains. A captivating journey into Mars' ancient past reveals a remarkable story. Approximately 4.5 billion years ago, Mars boasted a vast ocean covering 19 of its surface, rivaling the depth of the Mediterranean Sea. NASA's planetary models depict Mars in its prime, featuring a warm climate and an Earth-like atmosphere. Imagine arriving in an alien spacecraft on Earth. Chances are high that you'd land in water. Early Mars shared this water-centric characteristic, earning it the title of a water world. It was a world potentially teeming with life, even hosting waves twice as tall as Earth's due to Mars' lower gravity. A surfer's dream. Early Mars, with its water and thicker atmosphere, resembled an Arctic Ocean, ice-choked and frigid. Although farther from the Sun than Earth, 4.5 billion years ago marked Mars' most habitable era, akin to our planet during its formative stages. Interestingly, this was the time when life emerged on Earth. Despite its promising conditions, Mars' early ocean faced a tragic fate. Over 1.5 billion years, the Martian atmosphere succumbed to solar radiation, evaporating away and leaving only 13 frozen at the poles. The tantalizing question arises, could life have existed in that ancient Martian ocean? And if so, could anything have survived to the present day? The key lies in the possibility of finding liquid water on Mars. The Curiosity rover exploring Mars since 2012 has been a crucial part of this quest. Stunning images like the mesmerizing blue sunset challenge our perceptions of the red planet. The Mars Reconnaissance Orbiter's pictures of the Newton crater provide further insights into the remaining liquid water on Mars. Time-lapse sequences reveal streaks on the crater walls, possibly indicating the presence of water, albeit in smaller amounts compared to Earth's oceans or Mars' ancient water world. The pursuit of liquid water on Mars continues, opening the door to the tantalizing possibility of discovering life beyond our home planet. Mars' unique conditions are influenced by its axial tilt. While Earth's axis is stabilized by the Moon, acting as a gravitational outrigger, Mars lacks a large moon and is closer to Jupiter. As a result, Mars experiences a significant wobble in its axis, more than double that of Earth. Over 100,000 years, Mars's tilt wobbles by as much as 10 degrees, causing dramatic climate changes similar to but more extreme than Earth's ice ages. The harsh conditions, coupled with the absence of a stabilizing factor like Earth's moon, pose substantial challenges for the potential survival of life on the Martian surface. Our Sun, positioned at the center of the solar system, serves as the primary source of light, heat, and crucially, life. However, the trajectory of its future is a subject of inquiry for scientists who are peering into the vastness of space for answers. These scientists, akin to contemporary prophets, foretell a potentially apocalyptic fate for our Sun. The implications are astounding. The Earth's surface temperature is projected to reach levels capable of melting rock, and indeed, the entire planetary surface. Scientists are aware that at some point in the future, the Sun will undergo fundamental changes that will impact the planets in our solar system. Picture fast-forwarding 7 billion years ahead to witness the solar system's eventual demise. This foresight is possible because the transformations anticipated for our Sun are already observable in numerous other stars. Among these stars, some are referred to as solar twins due to their striking similarities to our Sun. The study of solar twins is crucial not only for comprehending the Sun itself, but also for gaining insights into the future of our solar system. In 2013, scientists identified a solar twin named Corot Sol 1, situated in the Monoceros constellation. Corot bears a resemblance to the Sun in terms of both mass and other characteristics. However, astronomers made a noteworthy discovery. Corot Sol 1 exhibited a lower concentration of lithium, a key element that facilitated an accurate determination of its age. It turned out that this star is slightly older than the Sun by a few billion years. By observing stars older than our Sun, scientists can glean valuable information about the Sun's future trajectory. As the Sun ages, it will undergo a significant increase in brightness. This heightened luminosity is a result of an ongoing internal transformation within the Sun, where two opposing forces engage in a constant struggle. These forces are akin to those influencing a hot air balloon, with the immense pressure of hot gas pushing up and outwards. Within the Sun, this pressure is generated by the process of nuclear fusion, where hydrogen is converted into helium. The Sun has sustained this fusion process for billions of years, marking its enduring battle against gravity. The Sun's life is essentially a perpetual conflict between gravitational forces attempting to compress the star and the outward thermal pressure exerted by the gas. The delicate equilibrium between these forces has kept the Sun stable for 4.5 billion years. However, with the passage of time, this balance is gradually shifting. As the Sun continues to fuse hydrogen, it produces an astonishing 600 million tons of helium every second. The alteration in density has a profound impact on nuclear reactions. As the core becomes denser, the rate of hydrogen burning increases, akin to turning up the burners. This translates to an escalation in the energy emanating from the core. Consequently, our Sun is becoming 10% brighter with each passing billion years. As it ages, the solar system experiences a rise in temperature. Scientists are aware that this ongoing process will eventually lead to significant consequences. The habitable zone, where Earth resides. This region orbits a band around the Sun and is characterized as the habitable zone because it maintains the ideal temperature for liquid water. This unique condition makes Earth the sole planet in the solar system where life can thrive. However, as the Sun intensifies its power, the habitable zone will undergo a shift. To glimpse Earth's potential fate 2 billion years from now, astrobiologist Professor Lynn Rothschild suggests looking to Venus. Venus is visible in the sky, positioned as the brightest object following the Sun and the Moon. Venus and Earth share a common origin, composed of similar materials and roughly the same size. The key distinction lies in Venus's proximity to the Sun, resulting in its higher temperature compared to Earth. Interestingly, despite being farther from the Sun, Venus is even hotter than Mercury. In 2006, the Venus Express probe was launched to study Venus's atmosphere in unprecedented detail. Analysis revealed a crucial clue among the clouds regarding Venus's elevated temperature. The Venus Express provided insights by detecting a significant amount of deuterium, a heavy form of hydrogen, indicating the presence of water in the planet's past. It became evident that Venus was once a drastically different world, resembling a beautiful water world not unlike Earth today. There existed liquid water, reasonable atmospheric pressure, and organic compounds on Venus in the past. The available evidence strongly suggests that Venus was once situated in the habitable zone, making it a plausible environment for life. Approximately 3 billion years ago, as the Sun's luminosity increased, it had a terrible impact on Venus's water. The rising temperature of the Sun had a cascading effect on Venus. As the Sun's heat intensified, the surface of Venus heated up, causing the water to transform into steam. Since steam is a greenhouse gas, it possesses the capability to trap solar radiation. Consequently, akin to a greenhouse, the temperature on Venus started escalating continuously. It appears that a runaway greenhouse effect played a pivotal role in making Venus the hottest planet in our solar system. While Mercury is closer to the Sun, it lacks both an atmosphere and water. In contrast, Earth possesses both of these essential elements. As the Sun becomes brighter and evaporates our oceans, the impact on Earth is expected to be significantly more severe than the currently observed effects of human-induced global warming. Over the course of the next 2 billion years, Earth's temperatures are set to soar, presenting a stark challenge for life to either adapt or face extinction. Approximately 500 million years from now, some regions could experience temperature increases of up to 20 degrees. This climatic shift will drive a profound evolution in life as we currently understand it. Similar to the way present-day animals adapt to survive harsh winters, future generations may employ comparable strategies to endure scorching summers. Consider a bear accustomed to hibernating in winter. A future scenario could reverse this pattern, with animals opting to hibernate during the scorching summers and remaining active in the cooler winters. Grasses may adapt by setting seeds in spring, ensuring the survival of the plant through the harsh summer, germinating when autumn rains return, and flourishing in the winter. In less than 1 billion years, the greenhouse effect is anticipated to intensify, causing temperatures to escalate dramatically. As the land becomes hotter, even winters may become inhospitable for most organisms. Warm-blooded large animals like bison, unable to adequately cool down in the increasing heat, may face extinction. In just over 1 billion years, the once thriving land could transform into a barren desert devoid of life. The atmosphere will heat up more rapidly than the water, leading me to predict that, similar to the ancestors of dolphins, the descendants of bison may need to transition from land to water for survival. Projections indicate that in 2 billion years, even the water will have disappeared. As it evaporates, Earth will increasingly resemble present-day Venus. In less than 3 billion years, the prevailing belief is that the scorching sun, combined with a runaway greenhouse effect, will likely eradicate nearly all life on Earth. But intelligent life may just find a way out. What sets us apart from other organisms is our possession of technology. This advantage may provide us with the option to migrate to other planets as Earth becomes inhospitable. As Earth heats up beyond tolerance, Mars could become a more viable habitat. The potential for life on Mars is uncertain, but with our technological capabilities, it's a possibility. Who knows? I have great faith in our descendants. In far-off galaxies, galactic invaders are at work. 3 times daily, a strange flash pulsates across our sky. It is hundreds of times stronger than all of the world's nuclear weapons put together. But it wasn't made by people, and if one happens close enough to Earth, it could wipe out all life there. Most people on Earth don't know about the possible dangers in space. Imagine this. A huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen, and then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burns to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light years away hit Earth, it could happen. Gamma ray bursts are the most bright blasts in the universe. They must have a huge amount of power because they're so far away and yet still so bright. As much energy as the sun will give off in its full 10 billion year life. We know there are many planets and many stars in the universe, so gamma ray burst could have wiped out a lot of different cultures. In the 1960s, this strange blast of radiation was first seen. At first, because these gamma ray bursts are so bright, most scientists thought they came from our own galaxy, the Milky Way. There are a few reasons for that. One of them is that if they are outside the galaxy, the energy is almost too much to believe. But back then, even the most powerful telescopes couldn't figure out where they were or how far away they were because the burst only lasted a few seconds and then went away. But then, scientists started to wonder about their afterglow. Most blasts in space leave a glowing trail behind that can last for days or even weeks. In the late 1990s, satellites with better optics and X-ray monitors were finally able to catch the afterglow of a gamma-ray burst. It became clear that gamma-ray bursts actually came from outside our galaxy, millions and billions of light years away. So, their power had to be really out of this world. The brightness of the gamma-ray burst is the same as that of 1,000,000 trillion suns. This huge explosion could wipe out all life on Earth. But why do they happen? We are very sure that a common gamma-ray burst is caused by the death of a star that is at least 10 times the mass of the Sun. And these kinds of stars aren't very common. When a very big star dies, it falls apart and forms a black hole. Black holes are made when a mass of matter shrinks to a point where it is so dense that light can't get out. But experts think that some of the star resists getting sucked into the center of the black hole. As a result, a high-speed spinning disk of matter forms around it. In a matter of seconds, plasma jets shoot out from the poles where it spins. These beams of energy unleash dangerous gamma rays into space. At the same time, the gamma-ray bursts are ejected, the collapsing star explodes or goes supernova to the extreme. Gamma-ray bursts are so bright because they take a huge amount of power and focus it on a very small area of the sky. Only one of every 300 gamma-ray bursts is directed toward us, so we only see one of those 300. Even if a gamma-ray burst happened not 100 but 1,000 light years away, the Earth could still be destroyed in a way that is similar to the end of the world. If a gamma-ray burst happens within 100 light years off the Earth, then it would be approximately 500 times brighter than the sun and made in gamma rays. The energy sent to the high atmosphere of Earth would be the same as if 100,000 megatons of nuclear bombs went off. The ozone would be depleted, we'd have acid rain, but we'd also have flash burns, incineration of vegetation, perhaps something resembling nuclear weather. So many species could go extinct all over the world. Now, the other side of the Earth would be a special place to be, because gamma rays don't go through the Earth, so you wouldn't get flash burned if you were there. However, the repercussions of altering the atmospheric composition and ozone depletion would ultimately come to the other side, and there, nobody knows what will happen. This nightmare scenario has a 1 in a trillion probability of occurring once in Earth's history. It's going to be a nasty day if you get caught in the beam, for the reason that this is extremely powerful radiation. You don't want to be in the vicinity of this sort of energy, since it has the potential to break down your own molecules. Currently, there is no way to protect humanity against gamma-ray bursts that occur in close proximity to Earth. They move at the rate of 186,000 miles per second, or the speed of light. By the time we detected them, they would have already struck our planet. Gamma rays bursts could pose a hazard to the Earth or to anything living that came within their born sight. Astronomers think that gamma ray bursts could be the cause of some mass extinctions on Earth. The one that happened 450 million years ago and killed off the Ordovician and Silurian species was probably the worst. Creatures that lived near the surface of the ocean were hit much harder than those that lived deep in the ocean. This is consistent with what would happen during a strong gamma-ray burst. In a galaxy the size of the Milky Way, gamma-ray bursts happen about once every few 100,000 years, according to astronomers. Even though they can be very bad, you have to be pretty close to be hurt by one. A gamma-ray burst happens about once every 5 million years, which is close enough to affect life on Earth. In other words, since the Earth was made 4.6 billion years ago, there have been about 1,000 events. So the chances of a close gamma-ray burst aren't zero, but they're low enough that you don't need to worry about them, unless you want to live for about 5 million years. Humanity obviously made it through the gamma-ray explosion unharmed, but this still demonstrates how far their effects may travel. Don't fret. Threats to Earth from gamma-ray bursts are extremely low. All of the closest contenders for gamma-ray bursts have been studied by astronomers, and none of them are either close enough or orientated in a way that would cause them to strike Earth. Therefore, what do you think? In our solar system, Earth shines like a sapphire jewel. We go about our daily lives without knowing that trouble could be coming from deep space. The routes that Earth and most other things take around the sun can be predicted. Most of the time, things are quiet and easy, but sometimes they get crazy and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted, jostled, and threatened by the object's energy and cosmic forces. The Earth is on a wild ride through space that is often very dangerous. When you're moving fast in on a predetermined path, you hope nothing crosses because there's nothing you can do. Rusty Schweickart used to be an astronaut, so he knows how dangerous things in space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He is sending out warnings about the risks of an asteroid named Apophis that is getting too close to be safe. Everyone noticed him right away because the probability of impact was quite high. In fact, it was significantly greater than any effect probability we had seen before. Schweickart has a scary example from real life that shows how bad an asteroid, even one smaller than Apophis, can be when it hits. June 30th, 1908, 7:15 a.m. A football field-sized object came hurtling down from space at about 34,000 miles per hour and made a stream of fiery gas behind it. Within minutes, the fireball hit Earth's atmosphere and burst violently near the Tunguska forest in Siberia. As a result, the explosion was the greatest ever recorded in the history of the planet. The explosion split the waves, which then set fire to 8 million trees in an area that was bigger than half of Rhode Island. Because the explosion happened in a place with few people, no one died directly from it. If that asteroid had hit just a few hours later, it would not have hit Siberia, but Europe. And if it had exploded in the air over one of Europe's biggest cities, 1 million people would have died. For the last 100 years, the Tunguska explosion has been shrouded in controversy. Many researchers now think an asteroid was the explosive trigger. Incredibly, it never even impacted the ground. Rather, it exploded 5 miles above Siberia's frozen ground. When it smacks into the lower atmosphere, doing about 50,000 miles an hour, it's like an egg smashing on the concrete. Energy equivalent to 15 megatons of TNT was released in the Siberian explosion, making it 1,000 times greater than Hiroshima. Over a huge city, this would be catastrophic. NEOs, or near-Earth objects, were the name given by scientists to these trespassers. They are comets and asteroids, leftover debris from when the planets formed. The Oort cloud is a part of the Kuiper belt that extends past Neptune and is where comets travel. Between Jupiter and Mars, asteroids take a curved path, but their orbital trip isn't always routine. We don't have to worry too much about asteroids because they circle in a somewhat orderly belt between Mars and Jupiter. But when one gets away and all that mass and energy is going toward Earth, that's when the astronomers start to worry. It's not uncommon for cosmic debris to be jolted out of orbit and headed for Earth. The majority of it is evaporated by our planet's dense atmosphere. A larger object, however, is able to break through Earth's atmosphere and crash to the surface. Asteroids are a real and dangerous threat if you wish to look to the cosmos for the powers that would have us dead. Just like it did previously, it will happen again. 65 million years ago, an asteroid the size of a small city plummeted down from the sky. It exploded in the Yucatan Peninsula, near the town of Chicxulub in Mexico, with a force of 100 million megatons of TNT. Here we see Earth hurling billions of tons of its crust into space, creating a blanket that blocks out sunlight, destroying the food web at its roots, and killing off countless species. The ferocious impact is thought to have been a factor in the extinction of the dinosaurs. We can think of asteroids as being bad things, but if it were not for an asteroid, we wouldn't be here today. Our mammal ancestors were running on their foot trying to avoid being appetizer for T-Rex. T-Rex gets taken out. Well, this opened up an ecological niche that allowed our mammal ancestors to evolve to something more ambitious than a route and outcomes the primates, and among the primates, we have people. But it's strange that the same kind of cosmic boulder that made it possible for humans to live could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects that were at least half a mile across, and what they found was unsettling. There are more than 850 NEOs near our vicinity. These asteroids are our nearest and most dangerous space friends. Finding these near-Earth objects is a bit like keeping an eye on storms. As you watch it day after day, you get a better idea of its path and can figure out where it's going, how big it is, and how fast it would hit the Earth if it did. By using telescopic technologies, NASA's Space Guard survey has detected over 90% of all near-Earth objects deemed harmful. These scary things could hit Earth with more power than all of the nuclear weapons on the world right now. Such an impact could trigger mass extinction. We wouldn't expect one to hit every few hundred, thousand, or millions of years, but if one did, it could wipe out different parts of the population. So there are events that happen very rarely but have big effects when they do. If they hit Earth, they would have impacts all over the world. They would not only wipe out a continent with very strong shock waves, but the debris would also be thrown into the air and land all over the planet, heating the air to 1,000 degrees. And all the vegetation all over the world where that happens would flash into flames. Smaller objects could also cause disasters. So Congress has asked NASA to find all NEOs with a diameter of 500 feet, which is as big as the Colosseum in Rome. A big object like that could wipe out a city or even a small state. Scientists are most worried about the asteroids they haven't found yet, not the ones they have found. Well, at the moment, there are about 2,000 objects that we can't say for sure won't hit Earth. We now have the technology to keep near-Earth objects from ever hitting Earth again. We can now literally start to change the local solar system to make it better for our life. The question is whether or not we will end up like the dinosaurs. It's hard to believe that the Earth has been around for more than 4.5 billion years because it's been through a lot since it was born. Asteroids that come into our orbit every year keep hitting our world like a boxer, but one day Earth could be knocked out. We've learned that near-Earth objects fly by us all the time, and we're getting more and more able to change our surroundings to help us stay alive. A rock in space named Apophis. In 2004, this pockmarked rock about 750 feet across came close to Earth. Now, it's scheduled to pass dangerously close to our planet again on Friday the 13th in April 2029. So, in 2029, Apophis will get closer to us than our Rome communication satellites that circle the Earth. If you are in the right place, you will be able to see Apophis pass by the Earth with your own eyes. That's how close that rock is going to get. You won't even need binoculars. Over 99% of the time, Apophis will miss the Earth in 2029. However, if it passes the Earth at an exact distance of 18,893 miles, it may pass through a gravitational keyhole, a small area in space that is only a half-mile wide. If this happens, Apophis could be thrown off by the Earth's gravity, which could change its path. It could make Apophis come back and hit Earth on April 13, 2036, 7 years later. The gravitational effect of the Earth would cause it to bend, cause the Apophis's orbit to enlarge to precisely the size, which 7 years later it will come around and hit the Earth. At the present time, Apophis has 1 in 45,000 chance of delivering a deadly blow in 2036. It's one thing to say that there's a 1 in 45,000 chance that it will hit the Earth, but what you really want to know is if there's a 1 in 100, 1 in 10, or 1 in 1 chance that it will hit the Earth. We have to look at Apophis the same way we look at any natural disaster. You know the date of the hit, when it happened, and the angle of the orbit, so you can make a map. It starts in western Siberia, cuts across and down the Pacific Ocean near California, goes through Central America, and ends in Western Africa. Scientists have come up with a scary idea about where Apophis could strike. With a force of more than 1 million megatons of TNT, the asteroid could hit the Pacific Ocean off the coast of California. Such an impact would make a hole in the water 5 miles wide and 9,000 feet deep. This would cause tsunamis with waves up to 50 feet high to hit the coast, resulting in unimaginable human loss. If a rock 1,000 feet across hits the ocean, that's not a good thing. For that kind of thing, Scientists are working on ways to stop such a cosmic strike from happening right now. A possible plan is to blow up an asteroid, but some people worry that this could make the problem worse by sending more pieces of the asteroid our way instead of just one. So, the new goal for experts is to change the path of asteroids that could hit Earth. Change its velocity by a 10,000th of a mile per hour so that it will miss the Earth instead of hitting it. If we know about an asteroid far enough in advance, we can change its path. Although a space probe has landed on an asteroid in the past, the most challenging idea is launching a manned mission. Once landing on the rock, astronauts could mount a radio transponder to track its whereabouts. Now, the United Nations plans to draft a treaty which will include who will be responsible for deflecting killer asteroids. If we are so careless that we keep doing nothing even though we know this is going to happen, that will be a real crime. Any asteroid hitting the Earth will require international disaster response. In addition, training is required in disaster and emergency management institutions and the public regarding the asteroid threat. It is important that everyone is aware of the level of threats and the potential to eliminate this threat. Apart from all these, amateur astronomers can work together with scientists to defend our planet. Amateur astronomers can help identify smaller and potentially destructive asteroids hidden in the universe. So would you like to be an amateur astronomer? Who knows? Maybe you can be one of the guards of our home. The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe and the strange and surreal paradoxes in what we think we understand. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Everything we know represents just 5% of the universe. What is the rest? Normal matter. Protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in space-time. This is known as the 4-dimensional space-time. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions, but these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional space-time can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the 4-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature? In certain situations, two particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where two particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics, as we know them, break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us onto new and unexpected ways, spurring us onto new heights of discovery and understanding. Imagine this. You're floating out in the calm, serene vastness of space, surrounded by billions of stars. Suddenly, you feel a pull, something you can't quite explain, a force stronger than anything you've ever encountered. It's not pulling you like Earth's gravity, it's pulling the very fabric of space itself. Welcome to the realm of a black hole. Black holes are among the most mysterious and fascinating objects in the universe. They form when the core of a massive star collapses under its own gravity, creating a point so dense that nothing, not even light, can escape its grasp. This boundary, known as the event horizon, marks the edge of the black hole, and once something crosses it, it's lost to the universe forever. But don't be too quick to fear them, I'd say with a smile. Black holes aren't cosmic vacuum cleaners waiting to gobble up everything around them. In fact, they don't go around eating stars or planets unless something gets too close. For the most part, they're just out there, minding their own business. The existence of black holes was once just a theoretical concept born from Einstein's general theory of relativity. But today, we know they are real. In fact, we've even seen one. Well, sort of. In 2019, the Event Horizon Telescope gave us the first ever image of a black hole, a supermassive one at the heart of a galaxy far, far away. And let me tell you, it's not just a hole in space. It's a doorway to some of the strangest physics we've ever encountered. You're probably thinking, how can we see something that doesn't let light escape? That's where things get interesting. We don't see the black hole itself. We see the light from material swirling around it, heated up as it falls into the abyss. That glow gives us a shadow of the black hole, a cosmic fingerprint of one of the universe's greatest mysteries. The birth of a black hole, the star that couldn't hold on. Let me take you on a journey back to the life of a star, a massive one. Imagine a cosmic giant shining brightly for millions of years, fueled by nuclear fusion deep within its core. It's a balancing act. Gravity tries to crush it, while the energy from fusion pushes outward, keeping the star stable. But like all things in the universe, this delicate dance can't last forever. Eventually, the star runs out of fuel. It's as if it's been holding up a heavy weight for eons, and suddenly, it can't do it anymore. The outward pressure from fusion weakens, and gravity, relentless and unstoppable, takes over. Now picture this. The core collapses, shrinking to a tiny, unbelievably dense point. This collapse triggers a spectacular explosion, a supernova, a cosmic fireworks display brighter than an entire galaxy. What's left behind, though, is far more intriguing: a black hole. But let me assure you, this isn't just any kind of collapse. The core compresses into something so small and so dense that its gravity warps the very fabric of space and time. What once was a massive star, millions of kilometers across, is now a singularity, an infinitely dense point in space. Around it forms the event horizon, the ultimate boundary beyond which nothing can return. This, my friends, is the birth of a black hole, a remnant of a star that once illuminated the universe, now a cosmic enigma. What happens at the event horizon? Let's talk about something truly extraordinary. The event horizon. This is the point where everything changes. Imagine standing at the edge of a cliff, but instead of looking down at rocks or water, you're staring into the unknown, where even light itself can't escape. The event horizon is like the ultimate no-turning back zone. It's not a physical surface you can touch. It's a boundary. If anything, whether it's a spaceship, a planet, or even a beam of light, crosses this line, it's lost forever. It's as if the universe says, that's enough. You're not coming back from here. But here's the real kicker. As you approach the event horizon, weird things start happening. Time itself begins to slow down. You see, near a black hole, gravity is so strong that it warps space-time. For an outside observer, it might look like you're frozen in time, hanging at the edge of the event horizon. But for you, time feels normal, at least until you cross the line. Once you do, Well, we can only speculate what happens next. The laws of physics as we know them no longer apply. Inside the event horizon, gravity is so intense that space and time are twisted beyond recognition. We call this the singularity, a point of infinite density, where even our best scientific theories struggle to explain what's going on. So, standing at the event horizon is like peering over the edge of the universe itself, into a place where time, space, and reality are fundamentally altered. It's a reminder that even with all our knowledge, the universe still holds mysteries we're only beginning to understand. The black hole's effect on space and time. Time dilation. Let's dive deeper into one of the most mind-bending effects of a black hole, how it plays with time itself. Imagine for a moment that you could hover near the edge of a black hole, right outside the event horizon. Time, as you know it, wouldn't tick the same way it does here on Earth. Near a black hole, time slows down, not just a little bit, dramatically. This effect is called time dilation, a phenomenon predicted by Einstein's theory of relativity. To an outside observer, you would appear to be moving slower and slower as you get closer to the black hole. In fact, if someone were watching you from a safe distance, they might never see you cross the event horizon. To them, you'd seem frozen in place, suspended in time. But for you, it's a different story. From your perspective, time feels normal. Seconds still tick by, and if you could somehow send a signal back to your friend, it would just seem like regular time to you. The closer you get to the black hole, though, the bigger the difference becomes between your time and the time outside. Now, here's where it gets even crazier. If you spend enough time near a black hole, just outside its event horizon, by the time you pull yourself back to safety, years, decades, or even centuries could have passed in the rest of the universe. It's like a one-way time machine into the future, but one you'd probably never want to use. This warping of time is one of the most fascinating aspects of black holes. It's a reminder that the universe doesn't always play by the rules we experience in our everyday lives. Near a black hole, the boundary between past, present, and future starts to blur. The biggest black holes in the universe, supermassive black holes. If you think the black holes we've talked about so far are impressive, wait until you hear about their bigger cousins, supermassive black holes. These aren't just stellar remnants. They're the giants lurking at the center of almost every galaxy in the universe, including our own Milky Way. These supermassive black holes are quite literally millions to billions of times the mass of our Sun. Let that sink in for a moment. Imagine something so massive that it warps not just the space around it, but entire regions of a galaxy. One of the most famous examples is Sagittarius A, the supermassive black hole right in the heart of the Milky Way. It's about 4 million times the mass of the Sun, and yet it's relatively quiet compared to some of its more active counterparts. In some galaxies, these titanic black holes are far more energetic. We call them quasars. A quasar is essentially a supermassive black hole that's actively feeding, pulling in huge amounts of gas, dust, and even stars. As this material falls in, it heats up to incredible temperatures and shoots out jets of energy so bright that they can outshine the entire galaxy they inhabit. These are some of the most powerful objects in the universe, visible from billions of light years away. But how did these black holes get so big? That's one of the great unanswered questions in astrophysics. Some scientists think they formed when galaxies first began to take shape, while others believe smaller black holes might have merged over time, growing larger and more powerful. What we do know is that these cosmic behemoths shape the galaxies around them. The gravitational pull of a supermassive black hole can influence the orbits of stars across vast distances. It's as if they're quietly orchestrating the motion of an entire galaxy, while we go about our lives on a tiny planet, completely unaware of the colossal forces at work. Black holes and the future of the universe. Now that we've explored the enormity of black holes, let's take a step back and think about their place in the grand cosmic picture. Black holes aren't just strange objects floating in space. They might actually hold some clues about the distant future of the universe itself. One of the most intriguing ideas is that black holes could be the last surviving objects in the universe. You see, everything in space, stars, planets, even galaxies, will eventually fade away. Stars will burn out, and over billions or trillions of years, what we know as the universe today will look very different. But black holes, they could stick around for an extraordinarily long time. There's even a theory, thanks to the groundbreaking work of Stephen Hawking, that black holes aren't completely eternal. According to Hawking, black holes can slowly lose energy through something called Hawking radiation. Over unimaginably long periods of time, this process could cause black holes to shrink and eventually disappear entirely. This isn't something that will happen tomorrow or even in the lifetime of our sun, but in the distant future, it's possible that black holes could evaporate completely. But before that happens, black holes will continue to shape the universe. They might grow by merging with other black holes, becoming even more massive. Or they might quietly influence the galaxies around them, slowly consuming matter that comes too close. So, could black holes hold the key to the universe's fate? We're still trying to piece together that puzzle. What we do know is that these cosmic giants are far more than just powerful gravity wells. They're part of the larger story of how our universe evolves. We may never fully understand them, but that's part of the excitement. The deeper we look into space, the more we realize how much more there is to learn. As we've journeyed through the world of black holes, from their formation to the way they bend time and space, to the enormous supermassive black holes at the center of galaxies, it's clear that these objects are more than just the stuff of science fiction. They are windows into the most extreme parts of our universe, revealing laws of physics that challenge our understanding of reality. Even with everything we've learned, black holes are still shrouded in mystery. Every time we peer closer, new questions arise. What happens inside the event horizon? Could black holes be gateways to other parts of the universe or even other dimensions? And what will happen when the last black hole finally evaporates? These are questions that continue to inspire scientists and spark curiosity in all of us. The study of black holes isn't just about understanding some distant phenomenon. It's about uncovering the secrets of the universe itself. So, next time you look up at the stars, remember that somewhere out there, a black hole might be quietly spinning, holding within it the answers to some of the biggest questions we've ever asked. And perhaps, one day, we'll unlock those secrets. Until then, keep wondering, keep exploring, and keep looking up. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you're interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch. The subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms. Protons and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals had been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars and all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. The search for life beyond Earth is really just getting started, but science has an encouraging early answer. There are plenty of planets in the galaxy, many with similarities to our own. Observations from the ground and from space have confirmed thousands of planets beyond our solar system. Our galaxy likely holds trillions, but so far we have no evidence of life beyond Earth. Is life in the cosmos easily begun and commonplace, or is it incredibly rare? Here are a few theories about aliens. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars, or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comment section below. Thanks for tuning in, and we'll see you next time. Is it possible for science fiction to become reality? I believe the reason Hollywood is so interested with the prospect of first contact with aliens is simple. It would be the biggest scientific discovery in human history. The problem is that our cosmos erects enormous hurdles to encountering extraterrestrials. It's almost as if the cosmos is trying to keep us from establishing first contact on purpose. We're looking for answers in the universe. Will we ever discover intelligent extraterrestrial life? Or are we alone? Arecibo Observatory. It blasted a strong radio message deep into space 45 years ago, launching our efforts to make first contact. The Arecibo transmission was the first communication or effort to connect with a hypothetical civilization outside our galaxy. That communication is currently en route to the M13 galaxy cluster, which is about 25,000 light-years distant. It carries data about our planet, our location, and even the composition of our DNA. The goal of this communication was, of course, to say hello, and also to raise the question, are we alone in the universe? But how likely is it that an intelligent alien culture is waiting for our message? Do you believe there is intelligent life in the universe? The answer is a loud yes. We know that life originated on Earth almost as soon as our planet formed. So why wouldn't it have occurred someplace else? How many extraterrestrial civilizations may we possibly contact if life has developed on other worlds? Frank Drake, an astronomer, devised an equation to assist in answering this critical topic. The Drake equation is a really remarkable effort to apply mathematical logic to the likelihood or potential of life beyond Earth. They also projected that there were about 10,000 intelligent civilizations in our galaxy. Since the Drake equation was initially developed, our knowledge of the galaxy has changed dramatically. Exoplanets are worlds found beyond our solar system. Exoplanets are being found all over the place. There are about 4,000 of them now known, and techniques are finding more every day. Scientists think what we've discovered is only the top of the iceberg. So, if the universe is so excellent at creating planets, maybe it can create the conditions for life to exist across the universe. We didn't know exoplanets existed when the Drake equation was developed decades ago. And today, scientists believe that there are more planets than stars in the cosmos. Even though life is very uncommon, there are many opportunities for it to emerge throughout the cosmos. As a result, it is quite possible that there is reasonably plentiful life in the cosmos, including an uncountable number of sophisticated extraterrestrial civilizations. This isn't science fiction, it's just basic probability. Most likely, there are many different alien cultures out there. So, don't you think it's a little strange that we haven't met yet? I think there are good reasons to think there are civilizations out there. Why haven't we found any other societies? One answer could be the sheer vastness of the cosmos. We live in the suburbs of the Milky Way, 75,000 light-years from the very edge. Radio signals travel the speed of light. With this speed limit, a signal sent to the other side of the galaxy would take 75,000 years to get there. The thing to keep in mind is that the galaxy is very big. Even if there are 10,000 civilizations in the galaxy, it's possible that the distances between the stars are so great that we'll never be able to talk to each other. So, imagine we sent a message into space 45 years ago, hoping to reach any potential aliens out there. Well, guess what? That message is still super far away from its destination because it's cruising at the speed of light. The place we're trying to reach is a whopping 25,000 light-years away. The vast size of the universe is a huge roadblock to making first contact. And that's a bit of a problem when it comes to reaching out to potential extraterrestrial buddies. The laws of physics are like a roadblock preventing radio signals from zooming across such vast distances. Turns out you can't break the speed limit of light. So even though there might be cool civilizations and life forms out there in our galaxy, they're just so darn far away. I hate to be the one to say it, but the universe is just too darn large. But fear not, we're not giving up. In fact, we're using the best tech on Earth to speed up the search. The Breakthrough Listen project is our superhero in this quest. Imagine high-tech facilities worldwide, radio telescopes, optical telescopes, all teaming up to scan the sky. They're focusing on the 1 million stars and 100 galaxies closest to us, making it the most epic search for alien chatter ever. So, if there's an alien aircraft around any of the 1,000 nearest stars, the Breakthrough Listen project is on it like a detective on a case. They've got the tools to catch any signals and make sure we don't miss out on an intergalactic conversation. Cool, right? Breakthrough Listen is like a cosmic detective trying to catch any signals from outer space. Right now, they're eavesdropping on the closest 1,700 stars to us, hoping to hear something exciting. But guess what? It's been pretty quiet so far. It's kind of like waiting for a phone call that never comes. It's frustrating because we haven't found any proof of alien civilizations yet. But here's the catch. Just because we haven't heard anything doesn't mean they're not out there. Breakthrough Listen is just getting started on its mission, and there's a whole lot more space in the universe to explore. Imagine it like searching for a needle in a cosmic haystack. It takes a ton of patience. Now, let's do some space math. If you use Drake's equation and figure there could be 10,000 intelligent civilizations, consider this. There are around 250 billion stars in our galaxy. That's like looking for one specific house in a city of 25 million houses. It's a massive task, a bit like making a bazillion cold calls. The universe is so vast that we might have to wait a really, really long time before picking up any alien signals. And even if we do hear something, it might be too late. Imagine getting a message from someone, but they sent it ages ago, and by the time it reaches us, they could be history. So, are we just fashionably late to the cosmic party? Could some aliens have come and gone already? Earth may have been around for a whopping 4.5 billion years, allowing us to evolve into a smart species. But in the grand scheme of the universe, we're just cosmic toddlers. Earth is super old, like over 4.5 billion years old. And guess what? It took all this time for us humans to become the cool, tech-savvy civilization we are today. But here's the kicker. There are star systems out there that have been around even longer than us. The universe itself is a whopping 13.8 billion years old. Wrap your head around that. We often think we're top-notch because we can build rockets and play with radio waves. However, if we met a civilization that's been around way longer than us, they'd probably be light years ahead in technology. There's this cool way of measuring how advanced a civilization might be. It's called the Kardashev scale. It sorts civilizations into 3 types based on how much energy they can grab from their surroundings. Type 1 can only use the energy of its home planet. Type 2 could potentially harness the energy of its entire solar system. And Type 3? Well, they're the big shots who could harness the power of a whole galaxy. And here's the buzzkill. We're not even a Type 1 civilization. We're somewhere between 0 and 1 on the scale. We can't fully tap into all of Earth's resources, so we're sitting at a modest 0.7. But hey, we're trying our best to catch up with the cosmic neighbors. Imagine an advanced civilization hitting Kardashev level 2 or 3. These guys could create mind-blowing structures that tap into the power of a star. Massive solar panels enveloping the entire star, a concept first dreamed up by Freeman Dyson. These cool structures are called Dyson spheres. Now, if other star systems or even entire galaxies have these epic Dyson spheres, could we catch a glimpse and finally make contact with these advanced beings? Here's the deal with Dyson spheres. They block almost all the light from a star, except for the sneaky infrared light. Why? Because those panels are soaking up sunlight and getting warm. And when things warm up, they give off thermal infrared light. So, we can play cosmic detectives by scanning the skies for this telltale thermal infrared signature to spot Dyson spheres. Back in 2015, NASA's Wide Field Infrared Survey Explorer scanned 100,000 nearby galaxies on the hunt for these advanced civilizations. They detected nothing. But here's the cosmic conundrum. The universe is crazy old, right? So, shouldn't other civilizations have had plenty of time to evolve? Well, maybe we just haven't noticed them yet. Imagine this. They're out there trying to send us a message, but it's like they're knocking on our door before our house is even built. Earth has been around for less than a third of the universe's 13.8 billion years. And humans? We've been strutting our stuff for just 300,000 years. That's a tiny window in the grand scheme of the cosmos to make that first contact. It's like trying to join a party, but you're fashionably late, and the party's been going on for ages. The hypothesis of natural filters in the universe posits that advanced extraterrestrial civilizations may have existed for a long time, but were eradicated by these natural filters. If extraterrestrial life exists, the question arises whether their forms and environments would be similar to those on Earth. This idea draws from the concept that certain conditions, whether astrophysical, biological, or societal, act as filters that limit the emergence and longevity of advanced civilizations. Possible filters include cataclysmic events, astrophysical phenomena, or self-destructive behaviors inherent to intelligent societies. If extraterrestrial life exists, its forms and environments might not necessarily resemble those on Earth. Life could evolve in diverse ways depending on the unique conditions of each planet. The variety of planetary environments and the adaptability of life make it plausible that extraterrestrial beings might have different biochemistries and physical characteristics. Rocky planets like Earth are considered ideal for supporting life due to their specific conditions. However, these planets are delicate and susceptible to various threats. And this fragility means the universe could filter out intelligent life quickly. One significant threat comes from violent stellar events such as gamma-ray bursts, which are powerful enough to sterilize planets over vast cosmic distances, potentially affecting entire galaxies. Imagine this. A huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen, and then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burn to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light years away hit Earth, it could happen. Even if intelligent species manage to survive these natural occurrences, there is another risk: self-destruction. Drawing from our own experiences on Earth, the development of technology has given us the capability to alter our climate and create weapons of mass destruction. This self-destructive potential poses a serious risk for advanced civilizations. It is plausible that technologically advanced societies may have a brief existence, as evidenced by our own history. The short lifespan of advanced civilizations could be a reason why there are so few observable ones at this point in time. The possibility arises that many civilizations may have emerged, but their existence was short-lived due to self-inflicted challenges. This scarcity of long-lasting civilizations could explain the limited opportunities for communication with extraterrestrial beings. Discovering remnants of an extinct alien civilization could serve as a profound warning for humanity. If we were to find evidence of a civilization that destroyed itself through pollution or conflict, it would be akin to looking at our own potential future. This sobering realization could provide valuable lessons for us on Earth, emphasizing the importance of avoiding similar pitfalls. In our quest for understanding the cosmos, we can only hope that some advanced alien species have managed to navigate the challenges posed by the universe's potentially lethal filters, offering a glimpse of long-term survival and prosperity. If we are lucky, there may be an extraterrestrial civilization that will come to visit us in the future. Imagine making contact with aliens. Sounds cool, right? But hold on, are we assuming too much? We tend to think that aliens are just like us, but here's the twist. They're not. We might be imagining them based on what we know about life on Earth, assuming they live on planets like ours. But guess what? Most of the universe might not follow our life and planet rulebook. So, could extraterrestrials even survive first contact with us and our planet? July 2019, a satellite on a test mission spotted a new alien world named GJ357d, about 31 light-years away. This super-Earth is over 6 times heavier than our cozy home planet. Now, what's a super-Earth? A terrestrial planet, but bulked up with more mass. More mass means more gravity, creating a whole different vibe compared to our Earth. Imagine aliens living on a super-Earth. The gravity there could be super strong. They might not be tall, but I bet they'd be super strong. Super-Earths are just one of the many wild things the universe cooks up. Who knows what other surprises are out there? The possibilities are as vast as the cosmos itself. The universe is a vast playground with planets of all shapes and sizes orbiting stars of various types and sizes, forming countless configurations. This diversity opens up a world of possibilities for life that is much richer and more varied than we ever imagined. However, we need to break free from the idea that extraterrestrial life will resemble us. If we're expecting beings with 2 legs like ours, we might as well abandon that notion. The truth is, life out there could be radically different. Consider this scenario. An intelligent alien species in our cosmic neighborhood wants to say hi to us. But here's the catch. If that alien evolved on a super-Earth or circled a red star instead of a yellow one, its biology could be so alien that it might never set foot or tentacle on our planet. Looking at life on Earth, it seems like it's tailor-made for our specific temperature, elements, and environment. Now, imagine an exoplanet with conditions conducive to life. It could still host life forms vastly different from what we're accustomed to. What if an alien world has a bit more potassium, is warmer than our average Earth, or has a thicker atmosphere? Each of these subtle differences could create an entirely distinct ecosystem. So, the big question is, can an alien organism truly adapt to our ecosystem when it lands on Earth? It's a cosmic mystery waiting to unfold. Welcome to our journey into the dark and mysterious world of black holes, the enigmatic powerhouses of the cosmos. Black holes, regions in space where gravity pulls so strongly that not even light can escape, have intrigued scientists and the public alike for decades. In this video, we'll explore what black holes are, how they form, and why they are crucial in understanding the universe. Join us as we dive deep into the science of black holes, uncovering their secrets and the groundbreaking methods used to study them. What is a black hole? A black hole forms when a massive star collapses under its own gravity at the end of its life cycle, squeezing all of its mass into an infinitely small point known as a singularity. Surrounding the singularity is the event horizon, often described as the point of no return. Once anything crosses this boundary, escaping the black hole's gravitational grip becomes impossible. Black holes come with fascinating properties. Firstly, their mass, which can be several times that of our sun, or as massive as millions of suns, when we talk about supermassive black holes at the centers of galaxies. They might also possess spin, rotating at immense speeds and influencing everything in their cosmic neighborhood by twisting space-time itself. Despite their dark nature, black holes are not just cosmic vacuum cleaners. They play a crucial role in the structure and evolution of galaxies, including our own Milky Way. Understanding these mysterious objects not only answers questions about the universe, but also about the fundamental laws of physics. The formation of black holes is a dramatic process, usually stemming from the remnants of a large star that has ended its life in a spectacular supernova explosion. Let's delve into how these mysterious objects come into existence. When a star significantly larger than our sun exhausts its nuclear fuel, it undergoes a dramatic transformation. Without the outward pressure generated by nuclear fusion to counteract gravity, the star collapses under its own immense gravitational pull. This collapse triggers a supernova, an explosion that outshines entire galaxies and ejects matter into space. For the most massive stars, what remains after this explosion is a core so dense that no known physical forces can stop its collapse, leading to the formation of a black hole. The core effectively collapses to a point of infinite density, a singularity where the laws of physics as we know them no longer seem to apply. But supernova remnants are not the only way black holes can form. In the vast expanse of the universe, black holes can also result from the direct collapse of massive gas clouds under certain conditions, skipping the star phase entirely. This process is thought to contribute to the formation of the supermassive black holes found at the centers of most galaxies, including our own Milky Way. Additionally, when black holes merge, a phenomenon observed through the detection of gravitational waves, they can form larger black holes, further adding to the diversity of these objects in the cosmos. In essence, black holes are born from the death of stars and other high-mass entities, playing a critical role in the cosmic cycle of matter and energy transformation. The detection of black holes. Detecting black holes is a complex task due to their invisible nature. Since no light can escape from them, astronomers must rely on indirect methods to prove their existence and study their properties. One primary method of detecting black holes is through their interaction with nearby matter. In binary systems, where a black hole is paired with a normal star, the black hole can pull in material from its companion. This material forms an accretion disk around the black hole, heating up due to intense gravitational forces and emitting high-energy X-rays before disappearing into the black hole. These X-rays, which can be detected by space-based telescopes, are a telltale sign of the presence of a black hole. Another method involves observing the orbits of stars around an invisible object. In the heart of our Milky Way galaxy, for example, astronomers have charted the orbits of stars around a region called Sagittarius A. The movement of these stars indicates they are orbiting a massive, invisible object, confirmed to be a supermassive black hole. Gravitational lensing is also a powerful tool for detecting black holes. This phenomenon occurs when a black hole bends the light from a background object, such as a galaxy or star, due to its extreme gravitational field. This bending causes the light to distort and magnify, appearing as rings or arcs from our viewpoint on Earth. The most recent and groundbreaking method is the detection of gravitational waves, ripples in space-time caused by some of the most violent and energetic processes in the universe. When two black holes spiral around each other and eventually merge, they emit these waves, which can be detected by facilities like LIGO and Virgo. These observations provide direct evidence of black holes and allow scientists to estimate their masses and other properties. Through these methods, astronomers continue to enhance our understanding of black holes, shedding light on some of the most mysterious objects in the cosmos. Black holes and relativity. Black holes are not only fascinating celestial phenomena, but also crucial elements in the study of Einstein's theory of general relativity. This theory, which revolutionized our understanding of how gravity works, predicts that massive objects can warp the fabric of space-time, and black holes are extreme examples of this effect. At the core of general relativity is the concept that gravity is not a conventional force, but a curvature of space-time caused by mass and energy. Black holes, with their immense mass concentrated into an infinitely small point, create profound distortions in space-time. This is why near a black hole, time seems to slow down and the paths of light and matter are bent, a phenomenon known as gravitational lensing. The Schwarzschild radius, or the event horizon of a black hole, is a direct consequence of relativity. It defines the boundary around the singularity, where the escape velocity equals the speed of light. According to relativity, nothing inside this radius can escape the black hole's gravitational pull, making the event horizon a perfect one-way exit from our observable universe. Black holes also challenge our understanding of space-time through their singularities, points where the curvatures of space-time become infinite. The laws of physics as we know them break down at these singularities, posing significant theoretical challenges and pushing scientists to think about quantum mechanics and gravity in new ways. Observations of black holes thus provide critical tests for the theory of general relativity. Events like the recent imaging of a black hole's shadow by the Event Horizon Telescope and detections of gravitational waves from black hole mergers offer unprecedented insights. These observations not only support the predictions of relativity, but also open new avenues for understanding the fundamental laws that govern our universe. Through their extreme nature, black holes serve as natural laboratories for testing ideas about gravity, space-time, and the limits of our physical laws, making them indispensable to the field of theoretical physics. Famous black holes and discoveries. Black holes might seem like uniform entities, but they are as varied as the cosmic phenomena that surround them. Some of the most notable black holes have unique stories that have significantly contributed to our understanding of the universe. Cygnus X1. One of the first black holes ever identified, Cygnus X1, became a key subject in the study of these cosmic objects. Discovered in the 1960s as a strong X-ray source, it was later confirmed to be a black hole through its interaction with a companion star. Observations of matter being pulled from the star into Cygnus X1's accretion disk helped astronomers validate the existence of black holes and provided a laboratory for studying extreme gravitational effects. Sagittarius A. At the center of our Milky Way galaxy lies Sagittarius A, a supermassive black hole with about 4 million times the mass of the Sun. Its presence was deduced from the orbits of stars at the galactic center, with their speeds and paths suggesting an extremely massive, invisible object. Sagittarius A offers a closer look at the dynamics of black holes at the centers of galaxies and their interactions with nearby stars and gas. M87. The black hole at the center of the M87 galaxy made headlines in 2019 when the Event Horizon Telescope captured the first ever image of a black hole's event horizon, or its shadow. This remarkable achievement not only provided visual evidence of black holes, but also confirmed general relativity's predictions at the edges of one of the most extreme environments in the cosmos. Gravitational wave discoveries. The LIGO and Virgo observatories have detected gravitational waves from several black hole mergers since 2015. These detections are crucial as they provide a new way of observing black holes and testing the limits of our physical theories. Each merger helps astronomers learn more about black hole masses, spins, and the history of galaxies. These iconic black holes and their studies have opened new windows into the high-energy universe, providing crucial insights into gravity, space-time, and the ultimate fate of massive stars. Unanswered questions and future research. Despite significant advancements in our understanding of black holes, they continue to be sources of profound mysteries and the subject of intense scientific inquiry. Here are some of the unanswered questions and the future research paths that scientists are pursuing to unravel these enigmas. Inside the event horizon, what happens inside a black hole remains one of the biggest questions in physics. Theories suggest that within the event horizon lies the singularity, a point where space and time cease to exist as we know them and where the laws of physics break down. However, the true nature of singularities and what happens to matter as it approaches this point is still speculative. Understanding this could lead to breakthroughs in our comprehension of gravity and quantum mechanics. Information paradox. The black hole information paradox poses a significant challenge to theoretical physics. It arises from the contradiction between quantum mechanics, which suggests information is never lost, and general relativity, which implies that information can disappear in a black hole. Resolving this paradox is crucial for a unified theory of quantum gravity, and research in this area is vigorous, with concepts like Hawking radiation and firewall hypotheses being explored. Formation and growth of supermassive black holes. The origins and rapid growth of supermassive black holes, especially shortly after the Big Bang, remain unclear. These black holes are millions to billions of times the mass of the Sun and are found at the centers of most large galaxies. Understanding how they formed and grew so massive in a relatively short period of cosmic history is critical for piecing together the evolutionary puzzle of the universe. Future missions and observations. Upcoming missions and observatories promise to shed more light on black holes. The Event Horizon Telescope continues to refine its observations to produce more images of black holes. Space missions like the James Webb Space Telescope and the planned Laser Interferometer Space Antenna, LISA, will explore the early universe and detect gravitational waves from black hole mergers across vast distances, offering new insights into their properties and behavior. Through these and other research initiatives, scientists continue to explore the enigmatic nature of black holes, pushing the boundaries of our knowledge and technology to solve the cosmos's most compelling mysteries. Thank you for joining us on this fascinating journey through the mysterious and powerful realms of black holes. We hope this exploration has sparked your curiosity and expanded your understanding of these cosmic giants. If you enjoyed this video and would like to dive deeper into the wonders of the universe, don't forget to hit the likes button and subscribe to our channel for more engaging science content. Your support helps us bring more exciting topics to light. Have any thoughts or questions about black holes? Or is there another cosmic phenomenon you're eager to learn about? Let us know in the comments below. We love hearing from you and are always looking to tailor our content to what you're most curious about. Remember, the universe is vast and full of wonders waiting to be discovered. Stay curious, Keep exploring, and until next time, keep looking up.
Imagine standing beneath a vast starlit sky. The stars shimmer like distant embers, scattered across an infinite canvas. The night feels timeless, eternal, and yet, science tells us this grand spectacle has a story, one that began billions of years ago. But stories don't just begin, they also end. And so we must ask, will the universe itself come to an end? If so, how? This question is both humbling and haunting. What lies ahead for the cosmos? Will it fade into eternal darkness, collapse upon itself, or be ripped apart in a catastrophic finale? The universe, vast as it is, holds secrets about its ultimate destiny, and these secrets are written in the language of physics, a language we are only beginning to decipher. I think of the universe as a ticking clock. At its birth, with the Big Bang, the clock was wound up, its hands set in motion. Over billions of years, it has ticked forward, creating galaxies, stars, and even life itself. But like any clock, it may one day wind down. The question is, what does that final tick look like? Is it the silence of a stopped clock, or an explosion that shatters the mechanism entirely? We are not the first to ponder this cosmic mystery. For centuries, philosophers, scientists, and dreamers have gazed at the heavens and wondered about the end of all things. Today, armed with telescopes that peer billions of light years into space, and equations that reveal the universe's hidden workings, we have begun to glimpse possible answers. These answers paint a picture that is as awe-inspiring as it is unsettling. In this journey, we will explore the universe's potential fates. We'll begin with its origins, tracing the story of its expansion and the forces that drive it. Then we'll examine the leading theories about how it might all end, from a slow, freezing demise to a dramatic collapse or an ultimate ripping apart. Along the way, we'll pause to reflect on what these scenarios mean, not just for the cosmos, but for us, the tiny beings who dare to wonder about it. So, take a deep breath and prepare to dive into the ultimate question. What is the fate of the universe? And what might it reveal about our place within it? The answers may not be comforting, but they are certain to ignite your sense of curiosity and wonder. Because in the end, contemplating the universe's story is, in many ways, contemplating our own. Part 1. Understanding the universe's expansion. The Big Bang and aftermath. To understand the fate of the universe, we must first revisit its beginning, the Big Bang. Imagine an unimaginable singularity, a point smaller than an atom, but holding all the energy and matter that would become the universe. About 13.8 billion years ago, this singularity exploded, not into space, but creating space itself. Time began, energy burst forth, and the universe began its grand expansion. Evidence of this explosive beginning is all around us. One of the most compelling pieces is the cosmic microwave background radiation (CMB), often called the afterglow of the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background radiation is a faint hum of energy that permeates the universe, a relic from when the cosmos was just 380,000 years old. It's as if the universe left behind an echo of its birth. Another key piece of evidence is redshift. When we observe distant galaxies, we see that their light shifts toward the red end of the spectrum. This redshift is caused by the stretching of light waves as the universe expands. Edwin Hubble's discovery of this phenomenon in the 1920s revealed a startling truth. Galaxies are moving away from us, and the universe is getting bigger. But what does this mean for the future? To answer that, we must understand not just that the universe is expanding, but how. Is this expansion slowing down, speeding up, or staying constant? These questions lead us to the mysterious force driving the cosmos's growth: dark energy. Think of the universe like a balloon. At the Big Bang, the balloon began to inflate. Over time, the rate of inflation has changed, influenced by the push and pull of different forces. Gravity, the force that pulls matter together, acts like a brake, trying to slow the expansion. But dark energy acts like an invisible hand, pushing the universe outward at an accelerating pace. This push and pull dynamic will shape the universe's ultimate fate. The story of the Big Bang is not just a story of beginnings. It's the first chapter in a larger cosmic narrative, one that sets the stage for the universe's possible endings. With the groundwork laid, we can now explore the scenarios scientists have envisioned for how this story might conclude. Current state: accelerating expansion. Today, scientists have discovered a surprising and critical truth. The universe's expansion is not just continuing, it's accelerating. This revelation came in the late 1990s when two independent teams of researchers studying distant supernovae noticed something unexpected. The supernovae appeared dimmer than predicted, indicating that they were farther away than they should have been if the expansion rate were constant. This was the first evidence of an accelerating universe. The force driving this acceleration is known as dark energy, a mysterious entity that makes up about 68% of the universe. Dark energy is not well understood, but it acts as a kind of anti-gravity, pushing galaxies apart rather than pulling them together. Unlike matter or radiation, which diminish as the universe expands, dark energy's effects seem to grow stronger over time, dominating the universe's behavior on the largest scales. To grasp this, think of a race car. In the early universe, the expansion was like a car speeding up a hill, gravity working against it. But now, it's as if the car has reached the top and is speeding down an endless slope, propelled by an unseen force. This accelerating expansion has profound implications for the universe's fate. If dark energy continues to dominate, galaxies will drift farther and farther apart. Eventually, stars will burn out, leaving behind a cold, dark cosmos. This scenario, known as the Big Freeze or heat death, envisions a universe where all energy is spread so thin that no meaningful interactions can occur. Yet dark energy also raises questions. What is it? Is it constant, or could it change over time? Some theories suggest dark energy might grow even stronger, leading to a Big Rip scenario where galaxies, stars, and even atoms are torn apart. Others propose it might weaken, allowing gravity to eventually pull everything back together in a big crunch. The accelerating expansion is a reminder of how much we have yet to learn about the universe. It challenges our understanding of physics and pushes us to ask deeper questions about the forces that shape our reality. As we explore the possible endings of the cosmos, this enigmatic force will remain at the heart of the mystery. Part 2. Possible scenarios for the universe's end. Heat death, the Big Freeze. Among the possible endings for the universe, heat death stands as one of the most somber and inevitable scenarios. Imagine a cosmos where all the stars have burned out, their light extinguished, leaving behind only faint remnants like white dwarfs, neutron stars, and black holes. The universe, once vibrant and filled with activity, becomes a dark, cold void. This scenario is rooted in the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. In the context of the universe, this means energy will gradually spread out, becoming less and less useful for sustaining processes like star formation or even chemical reactions. Over trillions of years, galaxies will disintegrate as their stars fade away. The remaining particles of matter will drift apart, their movements slowing as temperatures approach absolute zero. To picture heat death, think of a campfire on a cold night. At first, the fire blazes brightly, radiating warmth and light. But as the fuel burns away, the flames shrink, the embers cool, and eventually, only ash remains. The universe, in this analogy, is the fire, and its energy is the fuel. Current models suggest that heat death is the most likely outcome if dark energy continues to dominate and the universe keeps expanding forever. In this eternal expansion, distances between galaxies will grow so vast that even light cannot bridge the gaps. Without sources of energy or interaction, the universe will enter a state of maximum entropy, a heatless death where nothing can happen. Yet the thought of heat death raises profound philosophical questions. If the universe ends in stillness, does that render all its past activity meaningless? Or does the beauty of the cosmos lie not in its ultimate fate, but in the journey the stars, galaxies, and lives that once filled it with light and purpose? Heat death is not a sudden end, but a slow fading away, a whisper of the universe's former grandeur. It challenges us to reflect on time's inexorable march and the fleeting nature of existence. And while this gradual fading may seem bleak, it also offers a humbling perspective. The universe, like all things, follows its own natural course, a progression guided by laws we strive to understand. In the stillness of heat death, there is a quiet inevitability, a reminder of the fragility and transience of all that we hold dear. But perhaps the story doesn't truly end here. As with any grand narrative, every conclusion invites a new beginning. Might there be unseen mechanisms or phenomena yet to be discovered that could alter this trajectory? Could remnants of the universe's energy find a way to rekindle activity, defying the entropy that seems inevitable? The heat-death scenario leaves us with these haunting yet beautiful questions, compelling us to cherish the universe in its current, vibrant state. After all, we are fortunate to exist in a fleeting moment of warmth, light, and life, a brief oasis in an otherwise indifferent cosmos. The Big Crunch. Now let's imagine a universe where expansion doesn't continue forever. Instead, gravity, the force pulling everything together, takes the upper hand. Over time, this opposing force could slow the universe's expansion and eventually reverse it, causing everything to collapse inward. This scenario is known as the Big Crunch. Picture the universe as a cosmic elastic band. For billions of years, the band stretches, expanding outward as galaxies drift apart. But at some point, the pull of gravity becomes too strong. The band snaps back, drawing all the galaxies, stars, and matter back toward a single, dense point, a dramatic reversal of the Big Bang. This potential outcome depends on the universe's total density, the combined mass and energy it contains. If the density is high enough to overcome the momentum of expansion, gravity will halt the outward push and trigger contraction. Scientists refer to this as a closed universe. As the universe contracts, the distances between galaxies shrink, temperatures rise, and stars collide in violent interactions. Eventually, everything converges into an unimitably dense and hot state, similar to the initial singularity that sparked the Big Bang. The cosmos could end where it began, leaving behind a singularity, or perhaps igniting another cycle of expansion in what some call a big bounce. But is the Big Crunch likely? Current observations suggest not. With dark energy driving accelerated expansion, the universe's density appears too low for gravity to reverse the trend. Nevertheless, the possibility of a cyclical universe remains an intriguing idea, raising profound questions. Could time itself restart? Are we part of an eternal loop of expansion and contraction? In this vision of cosmic destiny, the Big Crunch is both an ending and a potential beginning of fiery collapse that might give birth to another universe, starting the story anew. The Big Rip. Imagine a universe where the fabric of space-time itself tears apart. This dramatic scenario, known as the Big Rip, envisions an ending driven by the relentless growth of dark energy. Unlike other endings where gravity or entropy dominates, the Big Rip unfolds as dark energy grows stronger over time, ultimately overwhelming every force that holds the universe together. In this scenario, dark energy doesn't just accelerate the expansion of the universe, it accelerates it exponentially. Galaxies move farther apart at increasing speeds. Over billions of years, this acceleration becomes so extreme that it begins to tear apart galaxy clusters, then galaxies, and finally stars and planets. Even atoms, the fundamental building blocks of matter, are ripped apart in the final moments. To picture the Big Rip, think of a piece of fabric being stretched. At first, the stretching is gentle, but as the tension increases, the fabric begins to tear at its weakest points until it completely unravels. In this metaphor, the universe is the fabric, and dark energy is the force pulling it apart. This cataclysmic end would unfold as follows. 1. Billions of years before the end, galaxies are torn from one another as dark energy's influence grows stronger than gravitational forces. 2. Millions of years before the end, individual galaxies disintegrate, their stars flung into the void. 3. Moments before the end, stars, planets, and even atoms are pulled apart, leaving a universe devoid of structure or matter. The timeline for the Big Rip depends on the behavior of dark energy. Current models suggest dark energy is relatively stable, but if it grows more potent over time, a property physicists call phantom energy, the Big Rip becomes a viable outcome. This scenario raises profound questions. What happens when space-time itself is torn apart? Does time cease to exist? Could remnants of the universe persist in some form, or would reality itself end in complete dissolution? The Big Rip, while speculative, reminds us of the sheer power and mystery of dark energy, a force we are only beginning to understand. It is both a terrifying and awe-inspiring vision of the universe's potential fate, one where the end is not a gradual fading or a collapse, but an explosive tearing apart of everything that has ever existed. Part 3. Philosophical implications and unanswered questions. What does the end mean for life? What happens to life when the universe itself approaches its demise? This question forces us to confront not just the physical realities of cosmic endings, but their implications for existence. Life as we know it is bound by the conditions of the universe, its laws, its resources, and its time. But if those conditions change drastically, does life have a future? Consider heat death, where stars extinguish and the cosmos cools to near absolute zero. In such a scenario, even the most advanced civilizations might struggle. Imagine building a fire in a snowstorm that grows colder and darker by the moment. How could life persist in such relentless entropy? Yet history shows us the resilience of life. On Earth, extremophiles thrive in the harshest environments, deep sea vents, boiling hot springs, and even radioactive wastelands. Could life, or something like it, find ways to endure in the distant future? Perhaps intelligent species could harness energy from black holes or tap into quantum phenomena beyond our understanding. The possibilities stretch the limits of imagination. But what if even these strategies fail? Does the end of life in the universe mark a true ending? Or is there meaning in the brief moments of light and complexity that life brought to the cosmos? These are questions not just of science, but of philosophy, forcing us to ponder whether permanence is a prerequisite for significance. Could advanced civilizations escape these fates? If the universe's natural course leads to oblivion, could advanced civilizations find a way to defy it? Science fiction often speculates on such possibilities, but even speculative ideas are rooted in the boundaries of physics. One idea is the Dyson sphere, a colossal structure built to harness the total energy output of a star. Such technology could extend the lifespan of civilizations, allowing them to thrive even as the universe dims. But what happens when there are no more stars? Perhaps more radical are theories of escaping the universe itself. The concept of parallel universes or a multiverse suggests that our cosmos might not be alone. Could a sufficiently advanced civilization open portals to other universes, transferring their existence to a younger, more hospitable cosmos? If so, they might survive not just the end of this universe, but potentially any number of universal lifespans. Then there's the question of time itself. Some theories propose that time is not a fundamental property, but an emergent one, tied to the universe's structure. If time ends with the universe, what does that mean for beings within it? Could they find a way to live outside of time, in a state of timeless existence? Or would such a concept defy even the wildest reaches of imagination? What these speculations reveal is the boundless creativity of the human mind. The universe's end might seem inevitable, but as long as questions remain unanswered, the door is open to possibilities we have yet to comprehend. Perhaps the greatest lesson is not about survival, but about the resilience of curiosity, the drive to understand and adapt, no matter how daunting the challenge. Is time an illusion? If the universe ends, what happens to the concept of time? To explore this, we must first ask, what is time? For most of us, time is a constant, flowing river, a relentless current that carries us from one moment to the next. But is this river real, or is it an illusion shaped by our perception? Theories in physics suggest that time might not be fundamental but emergent, a byproduct of the universe's structure and processes. If the universe ceases to exist, does time dry up like a river evaporating under a scorching sun? Or does it persist in some form we cannot yet fathom? Consider the Big Freeze, where the cosmos becomes a static, cold expanse. Without events or motion to mark its passage, what meaning does time have? In the Big Rip, where everything disintegrates into its smallest components, could time itself unravel, reduced to a meaningless concept? Time, in this sense, is deeply tied to change. It is the rhythm of the universe's dance, the beats of stars being born, galaxies colliding, and life evolving. Without change, the melody ceases. Does this mean time is merely an artifact of motion, a measure of the universe's activity? Or is it something more profound? The idea of time's end also raises philosophical questions. If time has a beginning and an end, is it a finite resource, like sand slipping through an hourglass? Or is it cyclical, a loop that resets with each new cosmic cycle, as some theories of the multiverse suggest? Could we ever exist outside of time, experiencing reality in a way that transcends our linear understanding? These questions remind us of the enigmatic nature of time. Whether it's an illusion, a dimension, or something entirely beyond our comprehension, its fate is inextricably linked to the universe's destiny. Time is the silent witness to all cosmic events, and pondering its end forces us to confront the ultimate mystery of existence itself. Are there cycles? Could the universe itself be part of an eternal cycle, dying and being reborn like a cosmic phoenix rising from its ashes? This idea lies at the heart of cyclic models, which suggest that the universe's end might not be a conclusion, but a prelude to a new beginning. One such model is the Big Bounce, a theory that envisions the universe contracting after its expansion reaches a peak. Instead of collapsing into a singularity as in the Big Crunch, the universe rebounds, triggering another Big Bang. This cycle of expansion and contraction could repeat indefinitely, creating an endless loop of cosmic rebirth. Another perspective comes from multiverse theories. These suggest that our universe is just one of countless others, each with its own birth and death. If universes can emerge from the remnants of others, could our cosmos be part of an interconnected web of existence, where endings are never absolute but merely transitions? The metaphor of a phoenix captures this concept beautifully. Like the mythical bird that perishes in flames only to rise anew, the universe could regenerate from its own demise. Each cycle would erase the past while laying the groundwork for future possibilities, an eternal dance of destruction and creation. But how might such cycles occur? Could remnants of the current universe, black holes, quantum fluctuations, or even dark energy seed the conditions for a new one? The details remain speculative, yet they ignite profound questions about the nature of existence. If cycles are real, is there a purpose to them? Do they follow a grand design, or are they random acts in an infinite cosmic play? Cyclic models challenge us to think beyond linear timelines and finite conclusions. They suggest a universe that, like a heartbeat, pulses with life and renewal. And while we may never witness these grand cycles, contemplating them reminds us of the vast possibilities that lie within the cosmos. Perhaps, in the universe's story, there are no true endings, only endless beginnings. Throughout this journey, we've explored the universe's potential fates. From the chilling stillness of heat death to the fiery collapse of the Big Crunch, the violent unraveling of the Big Rip, and the hopeful renewal of cyclic models. Each scenario presents profound questions about existence, time, and the nature of reality itself. But does the end of everything mean the end of meaning? Perhaps not. Meaning is not solely derived from permanence. It often lies in the fleeting, the transient, the moments that shape our experience of the cosmos. The stars that shine above us, the life that thrives on Earth, and the curiosity that drives us to seek answers, these are what define our place in the universe. As we contemplate the universe's story, we must embrace its uncertainties. The vastness of the cosmos humbles us, reminding us of our small yet significant role as observers and thinkers. Whether the universe ends in silence, destruction, or rebirth, its journey inspires awe and wonder. So, as you look up at the stars, remember this: the universe's greatest mystery is not just in how it ends, but in how it compels us to question, to dream, and to seek understanding. And in that pursuit, we find meaning not in answers, but in the act of asking.